slides, then I'll go ahead and start the lecture. All right. Last time we were discussing the linear model, and then I introduced lasso, where along with the residual sum of squares, you have a penalty term, which is the L1 penalty. So you basically add the absolute values of all the coefficients of the linear model multiplied by some constant alpha. And what we said, remember that we are not scaling, or this penalty term does not include the intercept. Okay, so if I have that equation here, this equation, so absolute values of omega 1 to omega p are added and multiplied by alpha, not omega naught, which is the intercept. All right, so I explained that alpha can be obtained by cross validation, which is in this case is fairly simple because we have only one tuning parameter or hyperparameter, whichever way you call it. But things can be more complex in more complex model, and eventually we will go to discussing random forest. So I had shown you the performance of the linear model, and I had shown you the performance of the lasso, and I had also shown you that lasso takes some of the coefficients to exactly 0. So let me now go to a different mod. So we are still talking about lasso, but we'll talk about this cross validation and how to find the optimum value of alpha. Okay, so the rest of the things remain as before. I have already shown you and shared this script with you. We are using the same data set, which is the heater formation data for the ABAC3 materials. Let me see. So these parts remain exactly as they are. Where it changes, so the split and the scaling remain exactly the same. This is the line that is different as compared to lasso. So recall that when you had lasso, we had supplied a value of alpha. In fact, the examples that I showed you, I'll go to that file now. So I'm on a different file. This is pure lasso. Yes. So we are defining the linear model as lasso with alpha equal to 0.01. Now, I do not know if that is a reasonable value. I should be using a larger value, a smaller value, what precisely. So this lasso CV, this model that you see here, this will find the optimum value for me. I can specify the range of values of alpha that my code scikit-learn should search, or I can just let it find its own value. In fact, if you are interested, I just leave that for you. You go to the scikit-learn user guide and find out what is the range over which it searches for the optimum value of alpha. Okay, and random state is just where it starts from the coefficients. And once you have defined, and CV equal to 5 means we are doing 5-fold cross validation. I explained cross validation yesterday. We have explained this earlier also. So, okay, so after fitting this, what we are printing, so we'll go up to this point now. We'll run this and see what we get. So we are printing the coefficients, the intercept, and the optimum value for alpha. So let's run it. Yeah. So you see the optimum, sorry, the optimum alpha that we got is 0.00069, which is very different from 0.01 I had set by hand in the earlier example. Now, because there is a randomness associated with it in how the data set is split, uh, if I run it a second time, I'll probably get a slightly different value for optimum alpha, because the test set and the training set would be somewhat different. See, I get 0.0007 this time, 76. But still, these values are very different from 0.01. So I have, it's very difficult to have a feel for, given a data set, it's almost impossible for you to have a feel for what should be an optimum alpha. So therefore, it is better to optimize it. So let us see what kind of results we get if we run the full model, do our predictions, calculate the performance matrix. Yeah. So I did not explain this relative error. So relative error is basically how the distribution of the error in the prediction looks like. So this is that prediction. So you see that the peak is pretty much close to zero, um, and very large deviations are very small in number. So that is exactly what you want, but that doesn't mean that you have acceptable performance. So the mean absolute error in the formation energy prediction is again 0.315 EV per atom, but the R2 score is still pretty poor. Last time we had got a number that was like 0.21. This time we got 0.23. These are not acceptable values. Okay, fine. So that is lasso. We'll do, and as I said, probably I should have explained that earlier, but nevertheless, we'll do it now. Is what is called ridge regression. So we are now discussing ridge regression. So this is one of the shrinkage methods. So shrinkage basically means that you are trying to reduce the values of your coefficients in a linear model and possibly taking some of them to zero altogether. Just let me check that everything is fine. Yeah. All right. So what is ridge regression? The ridge regression is just slightly different from lasso. So what you are minimizing is this residual sum of squares, this quantity, or the squares, I mean sum of the squares of the deviation of prediction from the true values, plus shrinkage or a regularization term. Now instead of putting a penalty on the L1 norm, we are now putting a penalty on the L2 norm of the coefficient. So sum over Wi squared. Again, alpha has to be, so it's very similar in spirit, but the result is sometimes very different, at least, conceptually, it's very different. So as I said, shrinkage penalty is applied only on the coefficients, not W naught. So both these models, whether lasso or ridge regression, why do we at all do this? What we gain is in terms of bias variance trade-off. If you have a small, or let's say zero value, alpha equal to zero, then it has large variance. You are fitting a linear model, and if you change your training data, if you have a different training data set, you will get a different line. So your coefficients will change significantly. So it has a large variance. So, but as you increase alpha, that variance reduces. It increases bias somewhat, but still overall there is a gain in terms of bias and variance, so you get better predictions. Now, ridge regression fits the model involving all the features, all the P features here, x1 to xp, and rarely, generally, you don't get any of the coefficients to be exactly zero. Unlike the lasso, where I showed you that some of the coefficients turned out to be exactly zero. So, ridge regression, it helps you in terms of bias variance trade-off, but lasso does an additional thing. Of course, it helps in bias variance trade-off, but it helps you do feature selection. When some of the coefficients are zero, you understand that those features are not even involved in the prediction of that particular property. So it yields a sparse model, which is easier to um, explain. Okay. We'll spend a few minutes understanding the difference between lasso and ridge regression. For this, we'll take a slightly different view of both the models, ridge regression and lasso. So what we are trying to do, so we have two parts in the penalty term, the loss function, if you wish, what we are trying to minimize with respect to the W's. One is the residual sum of squares, which is the same in both cases. In another case, we are trying to reduce the sum of squares of the W's for ridge regression. And we sort of think of it in a way that we have a certain value of S, certain quantity S, and sum of these W squareds has to be less than equal to S. Of course, S is related to my alpha. If alpha equal to 0, S can be anything. I can have any value of the coefficients. However, as alpha increases, the S decreases, because then it costs me to have very large values of W. The same thing for lasso, except that the S is related to the sum of mod of W's. Now, so we view S as sort of a budget for the coefficients. We can have only so much in terms of the values of the W's. We cannot go beyond that, so that either this quantity or this quantity becomes greater than S. So let us explain the situation in terms of a two-dimensional feature space. For lasso, the condition then becomes mod of W1 plus mod of W2 is less than equal to S. So how does, if I plot it on a 2D figure, what is this area mod of W1 plus mod of W2 less than equal to S? It will be a diamond shape like this shaded region here, centered on the centered at the origin in this space of here it is written beta 1 beta 2, but that's basically our W1 W2. So given a value of S, you have a certain size of this particular shape. S increases, the area increases, but the shape remains the same. That is one thing. Second thing, if I did not have the sort of shrinkage penalty, and if I only had the linear model, then given the problem, suppose, so I have an optimal solution for a set of values of W, and let's say that is in this case denoted by the point beta over here. Now, if we move away from this point, of course, the residual sum of squares increases. And how does it increase? So the contours of equal values of residual sum of squares would be ellipses in this two-dimensional space. Okay, so each of these ellipses as a constant value of that residual sum of squares. And as you allow larger values, you get larger ellipses. And then if S is very large, then this shaded area would be very large, and then this point beta would be within the shaded region, and that basically would be your solution, because then you are allowed to have those values of W. But as S shrinks, as S becomes smaller and smaller, this cannot be the solution of either the lasso, so we are talking of lasso. So the same beta cannot be the solution for the lasso problem, because it's now, this point is now outside the shaded region. So as you allow larger sort of RSS values, wherever this contour touches this shaded area first, that is the solution for a given S. And so if you understand that argument, then the next point is that for lasso, because this is a shape that looks like a diamond and it has sort of pointed edges, it is more often that it will hit or touch this shaded region at a tip, at a particular, on a particular, so at a tip means on a particular axis. So if it touches the shaded area on this axis, W1 is equal to 0. So that is when you get one of the coefficients equal to 0. So this is a two-dimensional example. You can sort of try to imagine it in multiple dimensions. So these ellipses would become, for 3D, if you go to three-dimensional space, it would become a ellipsoid. If you go to more, higher dimensional space, it will be hyperfigures, but of the shape of an ellipsoid. And these areas would also then, you have to consequently imagine such shapes in higher dimensional spaces, but the argument remains the same. There will be points along some axis, and those are the points where such ellipsoid figures or hyperellipsoid figures would touch this shaded area, and that is why you would have some of the coefficients exactly equal to 0. On the other hand, if you consider the Ridge regression, then the budget that you have for a given S is W1 squared plus W2 squared less than or equal to S, which is a circular region in 2D, a spherical region in 3D, and so on, hyperspheres in higher dimensions. And you don't have any sort of sharp points in such areas or figures. So therefore, wherever these ellipsoids touch it, it's unlikely that any of the coefficients would be exactly 0. So this is a sort of subtle difference between lasso and Ridge regression, and you now understand why. But lasso, the bottom line is lasso leads to some of the coefficients being exactly equal to 0. All right. So that's understanding the difference between lasso and Ridge regression. So with that, we'll now see how a Ridge regression functions. It won't be dramatically different. So let's run this. So now I'm looking at a Ridge regression code. And here my model is, I'll show where I do Ridge regression. So here it is. Let us start from a very small value of alpha. Let us say alpha equal to 1, so that the cost is not that much, the shrinkage penalty. So I run it. Yeah, so the mean absolute error is not dramatically different. The R square value is also not dramatically different. It's of the same order. But you see, now I want you to notice these numbers. These are the coefficients, the 30 coefficients, and none of these is actually exactly 0. Some are small, but not exactly 0 as you had in lasso. Let us try to increase alpha now. So we increase alpha to 10, an order of magnitude increase. I run it once again. All right. So these numbers have not changed very much, same or similar values. Let us look at the coefficients. Again, none of the coefficients is exactly 0. Okay, that is obvious. So we'll increase it further because this hardly takes any time. I can do it and show it to you. Let's look at the coefficients. Two, three, but none of them is reported as exactly 0. All right. Let us make this 1,000 and run it. All right. Probably it's not a very good value to use. The R2 score has decreased significantly. But let us look at the coefficients. They are small because I have a large lambda alpha, but none of them is exactly 0. So this just shows what I just explained to you, that lasso gives some of the coefficients to be exactly 0. Ridge regression does not. So with that, we'll conclude this discussion. This was to show you the simplest, the linear models, but these poor values of R2 score and other quantities, R2 score or the explained variance of the test set, we would like these to be closer to 1, but these are very small. So obviously, ridge regression or lasso or the linear model is not a good model for prediction of heat of formation based on the sign matrix eigenvalues. So we'll now go to a much more complex model. So I need to explain this a little bit, but I'll stop here for a couple of minutes. And if you have any questions, just type it in. I'll start in a minute. Okay, so now we go to what are called tree-based methods. Um, Again, we have discussed this. I'll once more go through some of these concepts and then I will show you an application of this. And then possibly I will leave you with some tasks. And I want you to do those as exercises. So there is this general class of methods called tree-based methods, and Dr. Mishra has explained in detail what tree-based methods are. Let me quickly recap some of the concepts. And the first thing we'll talk about is regression trees. So we have a regression problem at hand, and we are trying to apply tree-based methods to that regression problem. So suppose we have data for salary of some players. Okay, it could be it could be could be baseball, could be cricket, doesn't matter. Hits. So there are two sort of features on which salary or the value of a player depends. How much money that player gets depends on two quantities. One is hits. How many I don't even understand baseball. This was discussed in the context of baseball. So let us put it in the context of cricket, which we can follow more easily. So suppose how many boundaries, how many fours or sixes the player has hit. So that is hits, and number of years, how many years that player has been playing. So that is the figure on your left. So that is the overall data. So it's a two-dimensional feature space, and each one of those points represent the salary of a player. So this is my complete feature space with samples. Now the rule is to split this feature space into several regions. Let us say first, what we do is we split it along the years. Now, how do you decide whether to split along years or split along hits? I mean, these are questions we'll come to in a slide or two. But for the moment, to understand the procedure, let us say that we split this entire space by drawing this line here, this vertical line here at 4.5 years. So I divided into two regions, R1, which is given by this. So those samples for which the number of years is less than 4.5, and the region R2, the entire, so this is the first step. This entire region in the first step is R2, such that say is more than greater than or equal to 4.5 years. In the next step, I divide it along, so this right hand region into two parts by dividing the hits, dividing along the hits. So I take this axis, take a particular value, and then divide it into two parts, R2 and R3. R2, so this should be my R3, not R2. So eventually, I have three regions. This is R1, number of years less than 4.5. That's it. R2, where the number of years is greater than equal to 4.5, but hits is less than 117.5. And R3, where number of years is greater than 4.5 and hits is greater than 1.7.5. So this R1, R2, R3, these are in technical called terminal nodes or leaves of the tree. So we are creating a tree. So now we draw a different picture to represent the situation. At the top, we had all the data. Then we split it into sort of two branches. One for years less than 4.5, which is the left one. And we have something here. And this basically, I'll come to this, what these numbers are. And on the right are all those who have played for more than 4.5 years. And then again, we split this part into again two parts. One having number of hits less than 117.5, the others having hits greater than equal to 117.5. Now, what do we do with these regions? So this is where the general idea of prediction comes in. So I showed you a simple two-dimensional example. My feature space is p-dimensional, and I want to divide this p-dimension. Now, once I have divided my different samples belong. Now I want to make prediction. So for every observation in a region Ri, the prediction is the simple mean of the training observations in Ri. So if I have a certain number of training observations in Ri, I take the mean of those observations. Any test sample that falls in the same region will be predicted to have that average value. That is the prediction for that test sample. It's a very simple idea. So the prediction here is very, very simple. What you have to understand is how this tree is created in a multi-dimensional feature space, and what are the sort of nuances of it. And eventually I'll show you that this works much better than a linear model. So In general, the regions could have any shape, but for convenience, chosen to have be high dimensional boxes. So the cut that you do, cuts are always parallel to some axis or perpendicular to some axis, one of the axes. And what you are minimizing is, of course, again the residual sum of squares for a regression problem. So creating trees, that is how you create. Not that you have to do it, but you have to understand some of the things, because there are certain hyperparameters in the model that you might want to use. And if you don't have any idea about how these trees are created, then it will be difficult for you to fix those hyperparameters. So one of the simplest things you can do is to do what is called recursive binary splitting. Okay, so this is a very simple idea. It's a top-down approach. You start at the top and successively split the feature space. This is exactly what I showed you. You start at the top when all the samples are in a single region. You have only one region, the complete feature space. Then you split along one of the features. So basically, that what it means is that this axis is divided into two parts, one part on the left, one part on the right. And then this region is further divided by splitting this axis, the hits axis, one at the top, one at the bottom. But when it hits this line, you stop. Okay, you don't get here. You do a similar thing in a multi-dimensional space, and this is called recursive binary splitting. You choose a feature xj and a value s along. So feature xj is you want to split along the feature sj. And what is the value of xj at which you split? So here we split, first split was along years, and the value was 4.5. So that is the abstract form of that. So you split along the feature xj, and the value at which you split is s. Now, how do you decide these things? The simplest sort of brute force, naive way of doing it is you consider all features and all values of that feature, whatever exists in your data set, for splitting. And you see out of those all possible splits, the greatest reduction in the residual sum of squares. In the present situation, you have a certain value of the residual sum of squares. Now you consider all possible splits and you ask which is the split that leads to the greatest reduction in the residual sum of squares. You do that split, and that's how you proceed. Then in the next step, you again consider all features, all values, and find out which one leads to the greatest reduction, and go on like that. What do you get in the end? Now, recursive binary splittings lead to complex trees. There are many branches, many leaves. So the terminally, what you get. So if I go back to this figure, you cannot split this any further. So you have already split along one of the features. I mean, one feature, each of the features one time. So these are called leaves or terminal nodes. And this point before the second split, these are called internal nodes. Okay. So you'll have many branches, you'll have very complex trees, and what that does is, and remember, you are creating these trees based on your training data. So as you split, and what you're trying to, when you are training your model, you are trying to minimize the residual sum of squares for your training data. So if you build very complex trees in this fashion, what will happen is that you'll be overfitting your training data. So that's exactly happens with this recursive binary splitting. If you could build smaller trees with fewer states, it may have less variance, it may have higher bias, but still these will have lower bias, lower variance. So again, it's a question of bias variance trade-off. So one of the ideas that is used in this, these kinds of methods, this class of methods, the decision tree methods, is what is called tree pruning. So you grow a very large tree that is many splits and many leaves, and then you prune it to a subtree. So you remove some of the splits, build a smaller tree, starting from a very large one. Subtrees. Okay, after you have pruned some parts of the large tree. Now, what is there are many possible subtrees for a given tree. Now, what is the best subtree? One that gives you the lowest test error, which can be obtained by cross-validation. And I'll show you these bottom figures that you see here. For example, again in two-dimensional feature space. So notice the one on the right. So this one, this figure, okay, this you can obtain by doing a recursive binary splitting. So suppose the first split was this, then the second split was this, then a third split was this, then maybe or they have probably given a different sequence, doesn't matter. So the first split is this, the second split is this, the third split is again along the x1 axis, and the fourth split is along the x2 axis. So eventually you get like this. But look at the figure on the left. You can never arrive at a tree like this by recursive binary splitting, because in recursive binary splitting, you are always splitting along a particular feature all the way. But here you have shapes like these. Okay, so this cannot be obtained from recursive binary. So this possibly can be obtained by growing a large tree by recursive binary splitting and then doing some tree pruning. Okay, but we don't have to sort of. These are concepts that you should carry in your head, but yeah, the details of how exactly you get a figure like this, you don't need to worry. Okay, so far I have talked about regression trees, but regression is not the only kind of problem we do. We also do classification problems. So how do we handle classification problems in trees, and where is the difficulty? The difficulty is that we were deciding on the splits such that the residual sum of squares is reduced, the greatest reduction in residual sum of squares. That determines the next split. But there is no such thing in a classification model. So we have to come up with some measure using which we can decide how to split my tree. Okay. So what to minimize? There are two measures. You can use any one of those. Something called a Gini index, which is a very widely, and it's not just in machine. It's a statistic. Both these are statistical quantities. It's not like they are used only in machine learning. In economics, for example, it's a measure of, say, income inequality or wealth. So inequality, if you want to measure in place, in country, this is something that is used. But what is the idea? The idea is that you construct this quantity G. So first of all, it's a classification problem. So let us try to understand what we are doing here. It's a classification problem. So therefore, there are k classes. Okay? There could be 2, 3, or 4, or whatever number of classes in which we are trying to put our samples. And PMK is the number of training examples, or I think fraction of training examples, not the number, in the mth region. So mth region, and we have to split the feature space, and we are talking of the mth region in the feature space. In that mth region, uh, the fraction of training samples in the kth class. So I have up to capital K classes. The number of samples in the small kth class in the mth region of the feature space. So that is the number PMK. And then you construct PMK times 1 minus PMKs, you sum over all the classes, that's your Gini index. And you try to minimize that Gini index. Or you can try to minimize the entropy, which is a very similar measure actually. Otherwise, the idea is the same. You split along various feature axes. As I said, in general, these decision trees have large variance. And for example, one test could be, suppose you have a large enough data set to sort of train, so that you can split it into two halves and still train trees. So you split it into two halves and trained decision trees, two different decision trees. This could be very different. So the question is, and so therefore, if these are, they're coming from the same data, okay, same original data, you just randomly split it into two halves. You train two decision trees, and they look very different. So obviously, when you have very different looking decision trees, very different looking models, when you try to make predictions from those models, those predictions would also vary significantly. So that's your large variance. So how to reduce that variance? Now, how to reduce that variance, it brings us to the concept of bootstrapping, which was discussed in the earlier parts of the course. So let us try to recall what bootstrapping is. So let us focus on this part. Consider, suppose we have capital N independent random variables, and here this word independent is very important. Okay, whatever argument we are trying to give will not hold if they are not independent random variables. So we have capital N independent random variables z1 to zn, but each one of them has variance sigma squared. Now, if you consider the mean of these random variables, z bar, that's also a random variable because each zi is a random variable. But the variance of z bar would now be sigma squared over n. Okay, so there is a reduction in variance when you take an average of a number of independent random variables. Therefore, because we just gave the argument that using the same data by splitting into halves, if we train two different trees, there would be very different models. That is, my predictions would be very different. My model has large variance. So if I could train a large number of models, make different predictions, and then take an average, although each model would have large variance, because now I am taking average of their predictions, the variance of that prediction would reduce by a factor of n if I have n models, provided the models are not correlated, they are independent. So that is a crucial point that we have to remember, and that is a point that is relevant for the model that we are going to discuss. So the idea is that averaging over many models, the variance can be reduced. But how do I train many? I mean, I don't have enough data. I probably have enough data to train one model. I don't have enough data to train n number of models where n is large. So what do we do? Here, the idea of bootstrapping comes in. If you recall what bootstrapping is, suppose you have an original data set, and I'm just showing the values of, let's say, two features, x and y. uh, and here only three samples are shown, but of course you have large number of uh, samples here. You randomly draw a sample of size n. So if three here, if the size is three here, you randomly draw a sample of size 3, but you are allowed to draw a particular sample repeatedly. So you draw a sample, you place it back into the data set, then you draw another random sample. So you might get the same thing once again. So you could get 3, 1, 3, you could get 2, 3, 1, 2, 2, 1, etc. So you can create n random samples. So this is the method that's called bootstrapping. You are artificially creating n independent uh, data sets. And because now you have n independent data sets, you can train n different models. And if I'm predicting a quantity f, which depends on my features x, the end trees will make n different predictions. Okay, and the final result will be the average of this, and this method of this averaging is called bagging. So it's a bagging average of n predictions as applied to the regression model. Again, the question is, for a regression model, I can make predictions from the n models and I can take a simple average. So that's my final prediction. But what do we do for a classification model where the outcome is a qualitative thing? It's not a quantitative measure. So there, what you can do is there are various ways one can handle these situations. One can take a majority of votes. Suppose you have two classes, you have n number of models, and you see what do the majority of the models say. If they say class 1, then you put your test sample in class 1. If majority say class 2, you put in class 2. That's one way of doing it. Another way of doing it is some models give you the average probability that some test sample is in class 1 or a class 2 and so on. So different models will give you different probabilities, and you take an average of this. So you can do that as well, and I think that is what is implemented in scikit-learn. Okay, so now that we have done a recap of bootstrapping and we understand what bagging is, we are now ready to discuss the random forest model. So random forest, and why am I coming to this? Why am I discussing this model? Turns out that in the materials domain, perhaps in other domains also, I'm not so sure, but in materials domain, definitely, when your sample size is small, uh, the random forest works very well. It works better than neural network in many cases where your sample size is small. So therefore, it's interesting, and it's important to understand the random forest model and be able to use it for your task. Okay. Uh, further questions? Okay. So I'll spend a few more minutes here explaining what is random forest. Then we'll come back to these things again in the next lecture, and I'll show you code for random forest, and I'll ask you to do certain things over and above it. So as I said, okay. Um, what you do in the bagging model is you create a large number of trees. Okay, but it turns out that these trees are not all they are not uncorrelated, so they are not completely independent. Um, so one reason is that suppose one or two or few of the features dominate how the splitting goes. Okay. If a few features dominate the outcome, then you would try to split, or your policy would lead you to split along those features. So if you split along one of those features in the early stage, then the rest of it will follow a very similar trajectory in different models. So therefore, they'll be very correlated, they will be very similar to each other, and their predictions would also be correlated. So the condition that we said here, that variance goes down by a factor of n if the random variables are independent, that independence condition will not be satisfied. The random variables, the random outcomes, the random predictions would be correlated, and you will not have the level of reduction in variance that you would like to have. So, therefore, the task or the goal of the random forest model is to tweak the bagging model in such a way that it decorrelates the trees that you construct. You construct a number of trees, you take the average of a prediction of those trees, all those things remain the same, but how you create the trees, you do not follow the recursive binary splitting, you do something else. And that something else, that small tweak actually decorrelates different trees. Now they become statistically independent. Their predictions become statistically independent. Um, so one of the things that you do, I'll make this statement and stop here, and in the rest of it I'll take up next time. So what we said was that when we are trying to feature space, we consider all features, we consider all values of them, and then decide which where to split. Now, what you do in random forest is that you only consider a random sample of m features as candidates along which you want to split. So you don't even consider all the p features. You only consider m features, m typically smaller than p, and typical value chosen could be square root of p, which is much smaller than m, which is much smaller than p. Okay, so at each step you only try to split along square root p of the features which are chosen randomly. Okay, so you are not stuck with one, two, or few features which dominate the splitting. You give all features an equal chance so that you can split the feature space along those, and these leads to decorrelation of the trees. Okay, so I think that is where I would stop today. I will revise some of these ideas next time, and then I'll show you a code for a random forest regressor and see how you set these things, how you find the optimum values of various hyperparameters. So each one of these is a hyperparameter. You know how many times you split a tree, what is the value of m that you take, and many hyperparameters in a random forest regressor. You how you do a search hyperparameter space to get the optimum values, and then how that model performs. Okay, so that's all for today. If you have a question, you can type in. I'll give you a minute. Otherwise, we'll meet on Friday. Okay, there are no questions, so we end it here. We'll meet on Friday, same time.